Hi folks! The following video is our second one on bonding theories. I'm going to be discussing molecular orbital theory. Before diving into molecular orbital theory, I want to highlight some differences between sigma bonds and pi bonds. The shape of the orbitals that make up a sigma bond is going to have electron density symmetric about the bond axis. So let's imagine maybe a hydrogen molecule, H2, made up of two hydrogens bringing their s orbitals together. This is the simplest example of a sigma bond. We're going to imagine looking down the bond axis in a way that cuts through both of the hydrogen nuclei and rotating about that axis. Because each s orbital is spherical, you're not going to be able to tell if you've rotated it or not. You would say this bond is symmetric about this axis. Two more examples of sigma bonds are ones that are made up of hybridized orbitals overlapping, or ones where you have two p orbitals coming together with one lobe in to make a sigma bond. In each of these cases, if you looked down the bond axis, and then you imagine rotating about that axis, you would not see any difference upon rotation. In contrast, pi bonds, which are made up of side-on overlap of p orbitals, these will have electron density that is asymmetric about the bond axis. Here's an example pi bond where I've brought the sides of two p orbitals together. If you imagine looking down this bond axis, cutting through the two nuclei, and then rotating about that axis, you would be able to tell that you were rotating this bond. Therefore, we would say that this pi bond is not symmetric about the bond axis. The idea of molecular orbital theory is that in a molecule where you have more than one atom present, your electrons, rather than occupying atomic orbitals, they will occupy molecular orbitals. These molecular orbitals encompass all of the atoms of your molecule, and they're made up of the individual atomic orbitals from each atom. You could see how if you have more than a couple of atoms, this would get complicated really quickly. And if you've taken inorganic chemistry or a symmetry course, you may have seen these already, and just how complicated they can become. In this course, we're going to be selective and look at either just simple molecules or just key bonds within a molecule, rather than worrying about all of the molecular orbitals for a molecule. But one molecule that we can tackle is dihydrogen, H2. This one is convenient because each hydrogen only uses an s orbital to form bonds. You'll always have a y-axis of energy for your molecular orbital diagram, and you'll always put the atoms that you're bringing together on the left and right sides. Then you'll put the bond that you're forming and the orbital that you're looking at in the middle. So we have a hydrogen atom with one electron on the left, the same on the right, and we have our dihydrogen molecule in the middle of our diagram. So starting out, we're bringing together two hydrogens. These hydrogen atoms have the same energy starting out. They each have one electron in an s orbital. To form our hydrogen-hydrogen bond, we're going to think about combining these two orbitals together constructively, or adding them together. When we add these two orbitals together, you can just draw the two different hydrogens side by side with their s orbitals. Notice that my phasing is matching in this case. I have unshaded lobes drawn for each hydrogen. Also notice that now that I've formed this bond, I've moved the electrons from the individual hydrogens into this new lower energy orbital. Where molecular orbital theory may differ from what you've seen before is that we also have to consider destructive overlap of our hydrogen atomic orbitals. Essentially, thinking about subtracting one orbital from another. And you can think about this subtraction as changing the orbital's phasing. What this would look like, subtracting one orbital from the other, is that one of them is now going to be shaded and the other one is going to be unshaded. Similar to in the middle of a p orbital, when you go from shaded to unshaded in this molecular orbital, there's a node cutting between the two lobes. This is our site where there's no electron density present. Because I only had 2 electrons starting out and I've already used them to fill my lower energy orbital in the middle, this higher energy orbital that I've created is empty. Notice that the lower energy orbital that I created is symmetric about the bond axis. So I'm going to call this our sigma bonding molecular orbital. As a reminder, in the middle of my diagram, in terms of energy, are atomic orbitals from each individual hydrogen that these hydrogens are bringing together in order to form the bond. Our higher energy molecular orbital that we've created is called the sigma star antibonding molecular orbital. In this case, that orbital is empty. We'll use the term HOMO, which stands for highest occupied molecular orbital. In the case where you had more than 2 orbitals in your molecular orbital diagram, this would be harder to identify, but it'll always be the highest energy orbital that has electrons in it. And we'll use the term LUMO to describe the orbital that is lowest in energy and unfilled with electrons. LUMO stands for lowest unoccupied molecular orbital. I have 3 observations from the previous page that I just couldn't fit in very well with the amount already crammed in there. So I want to show you them before we move on. My first observation, and this will always be the case in molecular orbital theory, is that the number of atomic orbitals that you mix in is equal to the number of molecular orbitals that you get out. I'll often shorthand this as orbitals in equals orbitals out. Another observation that I want you to make is that by forming that sigma bond between the 2 hydrogens, we lowered the energy of their electrons. This is always favorable. And another observation that is more general as well is that the more nodes you create in your molecular orbitals, the higher in energy the molecular orbital is. Now let's consider a molecule that's just general A bonded to B, and we're going to assume that A is more electronegative than B here. This is different than our H2 molecule. The important thing to know for molecular orbitals is that the more electronegative an atom is, the lower in energy its atomic orbitals are going to be starting out. So let's construct our molecular orbital diagram for A and B coming together to form AB. Because A is more electronegative, its atomic orbital starting out is going to be lower in energy than B's atomic orbital. I'm making an assumption here that each atom is just using its s orbital to form a bond. This won't always be the case, and coming up soon I'm going to show you other ways of doing this that don't involve s orbitals, but this is the easiest one to start out with. I'm choosing to show A's atomic orbital in purple and B's atomic orbital in blue. So to get our lower energy bonding molecular orbital, I want to consider mixing these together in a constructive way, or adding them together in terms of their phasing. This will give me a lower energy orbital than either of the others starting out, and this is going to fill up with the electrons from A and B to give a pair of electrons in my sigma bond AB. Notice that my molecular orbital that I created is closer in energy to the atomic orbital A compared to the atomic orbital for B. When this is the case, you're going to have a larger contribution from the atomic orbital that it's closer in energy to. In this case, because the bonding molecular orbital for AB is closer in energy to A, I'm showing A as having a larger lobe in my molecular orbital compared to B. Now we need to consider the destructive overlap of our atomic orbitals for A and B. Imagine subtracting one from the other, and this is going to cause the phasing on one of the atoms to flip. I've chosen to draw this with the B side of the molecule shaded and A unshaded. Notice that I have to have a node through the middle of my molecule where I switch from shaded to unshaded. Also notice that I've drawn the lobe on B as larger than the lobe on A. This is because my antibonding molecular orbital is closer in energy to B than it is to A. So how this differs from the hydrogen molecule is that our atomic orbitals starting out are staggered, and this is going to make the lobes of our molecular orbitals different in size. Now we're going to imagine making a sigma bond from hybrid orbitals rather than atomic orbitals. This isn't true molecular orbital theory. We're taking some shortcuts here, but it's going to make it a lot simpler. The molecule we're going to look at is ethane, and we're going to ignore the hydrogens completely and just look at the carbon-carbon sigma bond. So each carbon in ethane is sp3 hybridized because it has 4 groups around it. And so in my molecular orbital diagram, I'm going to be forming my carbon-carbon bond from an sp3 hybrid orbital on each carbon. So starting my molecular orbital diagram, I'm showing an sp3 hybrid orbital for each carbon. Before bonding these carbons together, each of these orbitals has 1 electron in it. I'm going to imagine adding these orbitals together to get my lower energy bonding molecular orbital. What this will look like is bringing together the large and, in this case, unshaded lobes of my sp3 orbitals. This is going to give me really great overlap, and I'm going to fill up this bonding molecular orbital with 2 electrons, 1 from each carbon. Then I need to look at my anti-bonding molecular orbital, where I'm going to have a shading mismatch. When you bring together your mismatched orbitals, you're going to get some cancellation in the middle, at the node. Notice that toward the middle of the molecule, I have an unshaded lobe closest to a shaded lobe. In my bonding molecular orbital, my large lobes pointed in, and for my anti-bonding molecular orbital, my large lobes point out. To formally identify all of my orbitals, so what I started out with were hybrid orbitals on each of my individual carbons. My lower energy orbital is a sigma bonding molecular orbital, and my higher energy molecular orbital is a sigma star antibonding one. In my diagram, this sigma bonding orbital is the highest occupied one that's filled, or my HOMO, and the sigma star antibonding orbital is my LUMO, or the lowest energy one with no electrons in it. Now let's imagine making a polar bond from hybrid orbitals. Let's imagine making the carbon-chlorine bond of chloromethane. We're going to assume that carbon and chlorine are both sp3 hybridized, and this would make our bond made up from overlap of carbon's sp3 orbital with chlorine's sp3 orbital. So we're going to imagine starting out with one electron in carbon's hybrid orbital and another electron in chlorine's hybrid orbital. I'm putting chlorine's orbital lower in energy because it's more electronegative than carbon. When I bring these orbitals together constructively, I get out my sigma bonding molecular orbital. I'm bringing together the larger lobes of each hybrid orbital, and because my molecular orbital is closer in energy to chlorine than it is to carbon, I'm making my lobes on the chlorine side of the molecule larger. For my antibonding molecular orbital, I have my large lobes pointing out. My small lobes are pointing in, and their phasing is mismatched. This sigma star antibonding molecular orbital is closer in energy to the less electronegative carbon's hybrid orbital, so I make carbon's lobes in this antibonding orbital larger. So far, all of the bonds we've looked at, whether we made them from s orbitals or hybrid orbitals, they've all been sigma orbitals, or symmetric about the bond axis. Now let's look at a pi bonding molecular orbital diagram. We're going to imagine looking at just the pi bond of ethylene. Each carbon of ethylene is sp2 hybridized, and we're making our pi bond from unhybridized p orbitals on each carbon. For simplicity, we're completely ignoring carbon's bonds to hydrogen and the carbon-carbon single bond. Since we're only focusing on the pi bond, we're only going to think about a p orbital from each carbon. Before the pi bond is made, each carbon's p orbital has one electron in it. Before the pi bond is made, each carbon's p orbital has just one electron in it. I'm going to imagine bringing these two orbitals together side to side. When I bring these orbitals together constructively, you get what we usually think of as a pi bond. This contains our two electrons. In molecular orbital theory, when we bring these p orbitals together destructively, you get this mismatched orbital. Notice that here an unshaded lobe is across from a shaded one, and the same on the bottom of the molecule. Because of this, I've created a new node through the middle of my molecule, where there's 0 electron density present. If you calculate these orbitals, it turns out that rather than pointing sort of straight up and down from the atoms, these antibonding orbitals sort of splay away from each other, pointing out toward the side of the molecule rather than straight up and down, like in your bonding molecular orbital. I like to think of this as the phasing mismatch causing the orbitals to sort of repel each other a little bit, but I'm sure that's not really a scientific explanation. To formally classify all of our orbitals here, I started out with our 2 atomic p orbitals, one on each carbon. I brought them together side to side to make our bonding pi molecular orbital. And higher in energy, from destructive overlap, I generated an antibonding pi star molecular orbital. So far, we've only looked at systems where we're looking at a single bond with two atoms within our molecule. When you have delocalized systems, or ones with resonance, you may need to think about more atoms instead. An example where we think about 3 atoms at a time are in what are known as allylic systems. We have 3 options here. We could have an allylic cation, an allylic radical, or an allylic anion. Allylic refers to the position adjacent to a carbon-carbon pi bond. These 3 systems have different numbers of pi electrons, either 2, 3, or 4. Recall that in order to participate in resonance, your unpaired electron or your lone pair needs to occupy a p orbital, and because of that, it's going to become a part of the pi system. Because we're imagining p orbitals on 3 atoms combining, we're going to get 3 molecular orbitals out. Now that we have 3 atoms instead of 2, there isn't as good of a way to draw the atoms separately on either side and then together for the bonding and antibonding orbitals in the middle. So I'm just going to draw the molecular orbitals and not the starting atomic orbitals. Our lowest energy molecular orbital is going to be where you have all shading matches between the 3 p orbitals that are side to side. Notice on the top of my molecule I have fully unshaded lobes, and on the bottom of my molecule I have matched shaded lobes. As I mentioned previously, as you go higher in energy, you're going to have more nodes through your molecular orbitals. The next highest molecular orbital is going to have 1 node, and it's going to lie through the middle of the molecule. Your nodes are always going to distribute themselves somewhat symmetrically through your molecule. Because I have 3 atoms, due to symmetry, the middle atom's going to have the node cutting through it. Then on either side of the node, you're going to have a different shading. So looking at the top, I have unshaded, I cross the node, and I go to shaded. I have the same pattern on the bottom here. To get my 3rd molecular orbital, I need to think what's higher in energy than an orbital with 1 node? An orbital with 2 nodes. To distribute 2 nodes symmetrically in my molecule, I need to place them between the atoms. One between the left and center, and one between the right and center. Here as well, every time I cross a node, I need to have a shading change. So just looking at the top lobes in each case, I go from unshaded to shaded back to unshaded. Alright, so this is my general pi molecular orbital diagram for a 3-atom system. Now I want to consider which of these orbitals will be occupied or unoccupied depending on whether I'm looking at my cation, my radical, or my anion. As a reminder from before, my allylic carbocation has 2 pi electrons. I'll have 2 electrons occupying my lowest energy molecular orbital. My allylic radical has 3 pi electrons. This will completely fill the lowest energy orbital, and I'll put the 3rd electron in my middle energy orbital. And when I get to the allylic anion, I have 4 pi electrons. When I fill these 4 electrons into my diagram, filling up from the bottom, I get filled lowest and middle energy orbitals. Notice that for all 3 of these molecules, the very lowest energy orbital is filled, and the highest energy orbital is unfilled. The interesting stuff is happening in this middle energy orbital. Let's think about, for each of these species, what does this middle orbital represent? For the allylic anion, this middle orbital represents the HOMO, or the highest occupied molecular orbital. For the carbocation, the same orbital would represent the LUMO, or lowest unoccupied molecular orbital. We need some new terminology to describe the allylic radical. In this case, I have a new term, SOMO, which stands for singly occupied molecular orbital. You'll only get this when you have unpaired electrons. In summary, today's video gave an overview of molecular orbital theory. We looked at sigma bonds as well as pi bonds. I talked about cases where you have atoms bonded together with different electronegativities, and I talked about allylic systems, or 3-atom systems instead of our usual 2 atoms. That's it for this video. I'll see you in class.